Okay, so in this example from your homework, I'm going to show you how you could graph this rational function. Notice it is rational because it has a numerator and a denominator, and you have the variables all over the place, so it's not just a simple fraction. Now, in order to graph this rational function, remember there's some key things that we're on the lookout for. First thing is asymptotes, right? So to find vertical asymptotes, for example, those are some of the easiest. A vertical asymptote or a hole, it happens when your denominator becomes 0 for some reason. But the ones that are vertical asymptotes are the ones where you didn't have any cancellation. Now right now you can notice that this numerator does not factor nicely, so there's no cancellation, thus there's no holes. Therefore I can simply take the denominator, 3x plus 2, and I can say when would that give me a 0 in the denominator, because that would be the x value then when I solve for it, that would be problematic. So if you let 3x plus 2 equal 0, so you set your denominator equal to 0, you get 3x would equal negative 2, and if you divide that by the 3 next to the x would equal negative 2 over 3. So x equals negative 2 over 3, or about negative 0.6 repeating. That would be your vertical asymptote. So I can go to my graph, and here I could put like negative 1, and then negative 2/3 would be around here. So this is the part where the graph should be breaking apart at x equals negative 2 over 3. The graph should be breaking apart there, meaning it might go in two different directions. We're not sure yet. We continue finding our next type of asymptote. Now in this particular problem, we're looking for horizontal asymptotes or slant asymptotes. And if you remember, slant asymptotes are also known as oblique asymptotes, and they would occur when a horizontal asymptote does not happen, does not exist, and when the numerator's power or degree is exactly 1 bigger than the denominator's degree. The way I think I put this in the notes was n, the degree of the numerator, in this case is 2, and m, the degree of the denominator, is 1. So here n is bigger than m by exactly 1. If that happens, we do not have a horizontal asymptote, but instead we have a slant or oblique asymptote, and the way we find this is by long division. And I think I have an example in the notes and videos that you can watch if you need more practice with this. Okay, so to do that, we take our denominator of 3x plus 2, and we divide in to our numerator 9x squared plus 6x minus 5. And we're careful that when we do this long division, that we are going to ignore our remainder, and we'll talk about why that is in a moment. So to do long division of polynomials, just a quick review, we look at the leading term, and we say this leading term, 3x, times what gives me this leading term, 9x squared. 3x times 3x, good job. So traditionally in America, we usually set up long division this way. If you do it a different way from your country or from somewhere else, feel free to do that. Not here to confuse anybody. So we take that 3x and we multiply it by everything in front, every single term. 3x times 3x is 9x squared, and 3x times 2 is positive 6x. Once you do that, you subtract typically, or draw the line and change the sign. So if I were to draw the line and change the signs here, this becomes negative and this becomes negative now. So I now have 9x squared minus 9x squared, which cancel out, and 6x minus 6x, which also cancels. That doesn't usually happen, but if it does, our problem just got a lot nicer. So what we notice here is that we have 3x as our first term here, and now we have a 0. But if we were to bring down our next term of negative 5 and repeat the process, notice that 3x times what gives you negative 5? Can that happen? No, because you don't have an x anymore, do you? So this is what we would call our remainder. But if the whole process here is to figure out, as your x values get really big, what are your y values tending toward? If you were to put 5 over 3x plus 2 and add that on as your second term here, x getting really big would mean your denominator would approach really, really big numbers, which means you'd be dividing negative 5 by really, really big numbers, which means that it really is getting closer and closer to being meaningless, to 0. So we can ignore this. We can ignore it because it tends to go towards 0 as x gets really big at the extremes. So we don't need to worry about this part. All we care about is the non-remainder. So we would say that our slant asymptote would be this equation, y equals 3x. Now, do you remember how to graph a line? y equals 3x? Yeah, you hopefully do. Y equals mx plus b. Well, our b here is 0, so we would start at 0. And we would travel up 3 and right 1, because the slope here is 3, up 3, right 1. 1, 2, 3, right 1. We would have a point there at the location of 1, 3. Or if I had gone down 3, from 0 again, down 3, so now at the y value of -3, and left 1, that's over here, we would have a point at -1, -3 on the oblique or horizontal asymptote. No, sorry, not horizontal, oblique or slant, I apologize. So 0, 0 is where we started. We went up 3 and right 1, or down 3 and left 1. So we could now connect the dots of this horizontal, sorry, I keep saying horizontal, but I mean slant. Horizontal would have been a flat line, but this is a oblique or slanted asymptote. So now I have this slant asymptote, which was the equation y equals 3x. That's my slant asymptote. I have my vertical asymptote. And so let me show you again here what's going on. So we now have the graph partitioned into different regions. We have a region here, for example, or here, or here, or here. And we need to figure out where the graph is actually allowed to exist. One way to do that is by finding intercepts. So let's continue in the hunt for intercepts next. So to find x intercepts, for example, normally we would do that by letting y equal 0. Well, the y is your output. So if you let your output equal 0, that would mean that something over something gives you 0. In other words, simply set the numerator equal to 0. That means 9x squared plus 6x minus 5 equals 0. You could try to factor here, but it does not work. Instead, we could use the quadratic formula to solve. We did this earlier in the semester, where x equals -b, so -6, plus or minus the square root of b squared, so 6 squared, which is 36, minus 4ac. A is 9, c is -5. When you multiply 9 times -5, you get -45. So if you can't read under there, I have -6 plus or minus the square root of 36 minus 4 times ac, which was 9 times -5, or -45. All over 2a, 2 times 9, which will be 18. When I clean this up, so this is some simplifying from our earlier days, I'd have -6 plus or minus the square root of 36 minus -4 times -45 is going to be like 2 times 90, or 180. And it turns out to be a positive 180. 2 times 9 is 18. So now I have that denominator. When I add up 180 plus 36, I end up with 216. So I really have -6 plus or minus the square root of 216 over 18. Now you could put that in your calculator as separate pieces. You could put -6 plus the square root of 216 over 18. You get an answer of approximately -1.15. Or you could do -6 plus the square root, sorry, minus, that was minus, plus the square root of 216 over 18, and you get your positive answer of 0.483. 0.483. That's what I really need to draw my graph, right, for my x-intercepts. But if you wanted to practice simplifying radicals, this ends up being 216 is really 36 times 6. So you can actually put a 6 in front here and make it 6 square root of 6. And then you can divide each of these out by 6, and you'll get a nicer answer. One way you could have written the answer out would have been something like, eventually, -1 plus or minus the square root of 6 all over 3. But that would be if you decided to simplify the radicals and reduce by dividing everything by their shared factor. But for my graph, I can now go to my graph, and I can draw -1.15 approximately would be around here, and positive 0.483 would be around here. So I now have my x-intercepts on the graph. I now know which regions of the graph my graph should be in. It should be in something like this region, so approaching this vertical asymptote, but also approaching the oblique asymptote. So we see that happening here. And on the other side, since I have this x-intercept here, it should be approaching, the graph should be approaching the oblique asymptote, but it should also be approaching, notice, this vertical asymptote. So in order to do that, I'm going to have to cross the y-axis. So let's talk about again how to find y-intercepts. So let me get some room here. Sorry, the board got a little cluttered. This one's a little easier than finding x-intercepts this time. To find the y-intercept, we simply let x equal 0. In other words, f of the input 0. And when I do that, 9 times 0 squared is just 0, plus 6 times 0 is just 0 again. So don't I just get minus 5 up there? Try it yourself. For the denominator, if I let x be 0, 3 times 0 is 0, and 0 plus 2 is just 2. So I'm getting negative 5 over 2, also known as negative 2.5. Okay, so this would be my y-intercept. You could also give the point 0, negative 2.5. So that means negative 1, negative 2, negative 3. Right around here is my y-intercept at negative 2.5. Now I play connect the dots so that I'm approaching both the oblique asymptote after I go through the x-intercept here. Then I approach the vertical asymptote after I go through the y-intercept of negative 2.5. So I now have my graph sketched. Now, if you wanted to get an even better sketch, you could pick random test points, right? You could say, well, what's happening when x is negative 5? And you could put negative 5 in, plug it in, and see that you're somewhere down here. Or you could say, what's happening when x equals positive 5, somewhere over here? Put 5 in for your x value, get a number, it'll be something up there. So you can do as many test points as you need to get a decent sketch, but typically the x-intercepts, the y-intercept, and the asymptotes get you started. Okay, I hope that helps. This is our sketch that we're looking for here, and we did it using the intercepts and the asymptotes. I hope that helped. If you still have questions, you know you can reach out to me or the tutors. All right, good luck, and have a nice day practicing, because remember, math is not a spectator sport. See you next time.